Understanding general relativity, the warping of space-time. General relativity, the universe's invisible fabric. Imagine you're standing on a trampoline. When you step onto it, the fabric bends under your weight. Now, roll a small ball across the surface. It doesn't move in a straight line anymore. Instead, it curves towards you, not because you're pulling it, but because the trampoline is warped.
This is exactly how general relativity works, but instead of trampolines, we have space-time, the invisible fabric of the universe. Instead of people stepping on trampolines, we have massive objects like planets, stars, and black holes bending this cosmic fabric. And just like the ball rolling toward you, objects move along the curves created by this bending. Before Einstein, gravity was thought of as an invisible force pulling objects together, like a magnet. But Einstein's genius was realizing that gravity isn't really a force. It's the effect of space and time bending around massive objects. For example, picture the sun sitting in the middle of a vast invisible sheet of space-time, stretching it like a bowling ball on a trampoline. The planets, including Earth, aren't being pulled by some magical force. They're simply following the curves in this fabric, moving in their orbits like marbles rolling around the dip in the trampoline. Even light, which normally travels in straight lines, bends when it passes near a massive object. We can actually see this effect in space. When light from distant stars passes near the sun or massive galaxies, it bends around them, creating a cosmic magnifying glass known as gravitational lensing. This allows astronomers to see galaxies that would otherwise be hidden behind other celestial objects. Gravity doesn't just affect space, it affects time too. Near a massive object, time slows down. If you lived near a black hole, a single hour for you might be years for someone far away. This isn't just sci-fi, it's been tested. Astronauts on the International Space Station experience time slightly faster than we do on Earth because they are farther from the Earth's gravity. The effect is tiny but measurable. And GPS satellites must correct for this time difference, or your phone's navigation would be off by miles. Perhaps the most extreme example of Einstein's theory is the black hole, a region where gravity is so intense that space-time is curved infinitely. Anything that crosses its edge, called the event horizon, is trapped forever, unable to escape, not even light. Astronomers confirmed Einstein's predictions when they captured the first ever image of a black hole in 2019. The glowing ring around the dark center is light being bent by the black hole's immense gravity, exactly as Einstein's equations predicted over 100 years ago. General relativity isn't just a cool theory, it's how the universe actually works. It explains why planets orbit stars, how light bends around galaxies, why time moves differently depending on gravity, and even how GPS in your phone stays accurate. So the next time you look up at the stars, remember, you're not just seeing distant suns, you're witnessing the grand, invisible curves of space-time itself.